When you order a package online, you can track it as it moves from a warehouse, across a major highway, down your local street, and right to your front door. Inside your computer, an invisible, highly organized logistics network operates exactly the same way. Your computer consists of dozens of separate parts: memory chips, graphics processors, and storage drives. How do all these distinct pieces talk to each other without their signals dissolving into total chaos? They rely on a highly specific road system. In computer hardware, we call this a bus. While the name might suggest a vehicle, a computer bus consists of the physical wires and printed copper circuits running along a motherboard surface. Everything your computer accomplishes, from playing a video to calculating a spreadsheet, relies entirely on this physical infrastructure to move electrical signals from point A to point B. Just like a real road system, these digital roads carry specific traffic. There are 4 main elements traveling on a bus: data, which is the actual cargo; addresses, which indicate the final destination; control signals, which act like traffic lights coordinating the flow; and power, the fuel keeping the components running. Beyond the items shipped, the system follows specific directional rules to manage how that traffic moves. Some pathways use what is called simplex transmission. This is a strict one-way street. Information can only flow in a single direction, from the sender to the receiver. Other paths use half-duplex transmission. Imagine a narrow, single-lane bridge where traffic can travel in both directions, but they must take turns. One side waits while the other side crosses. Finally, there is full-duplex transmission. This is a modern two-way street where data moves simultaneously in opposite directions without anyone having to wait. The directional capacity of a specific bus dictates how quickly components can hold a conversation. If 2 parts need to constantly share information back and forth, a full duplex path ensures they aren't stuck waiting at a digital red light. The volume of traffic a road can handle is known as data width, essentially the number of lanes available for bits of data to travel side by side. Parallel buses are designed like a wide, multi-lane highway. Because they have multiple wires running next to each other, they can transmit an entire group of data bits simultaneously. But parallel buses require a lot of physical space. Furthermore, over long distances, signals traveling side by side can cause electrical interference with one another, corrupting the data. That brings us to serial buses. Instead of a multi-lane highway, a serial bus is a single, super-fast bullet train. It transmits data over a single path, one bit exactly after the other, timed perfectly. Because a serial bus only uses a single path, it eliminates side-by-side electrical interference. This allows it to run at incredibly high speeds, often carrying a higher volume of data over time than wider parallel paths. Computer engineering requires constant compromise. Designers choose between parallel and serial connections based on exactly how much space they have, the distance the data needs to travel, and the speed required. Now let's look at how these roads connect different locations. Point-to-point buses act like private driveways, forming a direct, exclusive connection between exactly 2 devices. This diagram illustrates these connection types. On the left are point-to-point setups, like a printer plugged into a USB port. On the right are multi-point or broadcast buses, operating like public roads shared by multiple computers on an Ethernet line. With all these shared roads and complex intersections, the cargo needs clear directions. In computing, we use instructions. These act as strict shipping labels, telling the system to exactly what to do with the data. This graphic shows the instruction format. On the left is the opcode, the action verb dictating the task, like add or store. On the right, the bracket points to the operands, the noun. These provide specific memory addresses where data is located. Without these perfectly formatted shipping labels, millions of electrical signals would simply bounce down the bus lines with no purpose and no final destination. Let's put this entire logistics network together in real time. Imagine you click your mouse to open a new application. That single physical click instantly generates a system instruction. It creates a precise shipping label, complete with an opcode telling the system to open, and an operand pointing directly to the application's memory address. This specific instruction merges onto a fast point-to-point serial bus, flying down the physical copper trace on your motherboard directly toward the central processing unit. Because the instructional label is perfectly formatted, it arrives at the processor ready to go, and the application opens on your screen a fraction of a second later. Every click and keystroke is the result of millions of flawless logistical deliveries moving along physical pathways at the speed of light. Thank you for joining me to explore the city inside your computer.